Hello everyone, my name is Mandar Yawalkar. My project partner Laurel Norris and I worked on the MRCEC prototype as a part of Subteam 1. For the prototype, the hydrofoils were manufactured with foam pieces, metal ribs, and tail spar. These were then laid up with carbon fiber to ensure low friction and waterproof exterior. During the layup process, the leading edge of the hydrofoils picked up slight imperfections. These will be sealed using fiberglass or carbon fiber. The spokes were manufactured using high-density foam molds. The molds underwent a carbon fiber layer process to form a 1.5 millimeter thick shell. The spoke hubs will be trimmed and connected using 3D printed inserts. Moving further, the next steps would be to seal the edges of the spokes and installing the PVM mechanism. This will be followed by the assembly of the frame and the shaft subsystem.
Hello, we are Jakob Harbers and Simon Vo, and today we'll be talking about our wave energy conversion system. This slide shows our preliminary designs for the spar section of the system. The float design can be seen here. This slide shows a brief animation of the oscillation motion of the float.
Using MATLAB Simulink, we have devised a diagram that allows us to test forces, float height, water level, and power generated with varying inputs. Here, as shown on the right-hand side, is our power graphs with a dampened coefficient of 1,000 newton seconds per meter. We also plot average power generated at varying damping factors at both 200 kilogram float mass and 500 kilogram float mass. We can see that they have different ideal damping factors in order to generate the most average power.
Our future action items will be to develop a design for a sprocket generator system, further develop our engineering model, and refine our CAD models and animations using more data.
So we're group 3 and we're working on a portable water turbine device. The problem is the armed forces need a system that can move a portable hydroelectric generator from one point to another. That's the kind of device that our team has been focusing on. So we're focusing on a lightweight design and easily transportable from a person or a vehicle from one location to another. So our solution is a vertical axis hydrokinetic turbine, or VHAT, and the concept model is shown to the right, with a debris shield and for additional modular bases to configure based on what kind of environment is needed. Power calculations have been connected as well, and most of the parts can fit inside of a small PVC tube like this, which allows for greater mobility and easily storable to move from one location to the next. This is important so we can generate reasonable amount of power quickly and not have to rely on diesel generators that are used currently.
Hello, we are Subteam 4 and the problem we are addressing is how to raise the turbine up and out of the water for maintenance, as well as submerge the turbine to the desired operating depth. This picture shows the previous design, which had a large pontoon-like float to keep the turbine in one place. It had a large surface footprint and a very complicated system to lift the heavy turbine out of the water. The design we came up with is a ballast system consisting of 2 large ballast tanks and 1 water pump. The water pump pumps water into the tanks to lower the turbine and pumps water out of the tanks to raise the turbine up. This solution is better than the previous solution because the surface footprint and the complexity are lowered. You should note that these pictures are pictures of our proof of concept and not the full scale.
We are subgroup 5 working on the hydraulic transmission system. At the beginning of the project, we were given this schematic, and as the project went on, we had to make changes as things came up. Mainly, we had to remove the accumulator, add a filter, and put the pressure relief valve into parallel. Then we had to size and find parts that weren't already bought for us. So we had to size the check valves so as to prevent cavitation, the pressure relief valve to keep pressure below the maximum, and a reservoir to hold the oil.
We then had to find a filter to reduce contaminants, a braking resistor to dissipate the energy produced in the generator. We needed oil to run through our hydraulic transmission as the working fluid, and then we needed a coupling to couple the motor to the generator. We were able to source all these parts and get them ordered, so we now have all the parts that we need to work on our hydraulic transmission. So from here we should be able to assemble it and then we'll test it in conjunction with the completion of the turbine side when that happens. And the initial test will happen in the civil engineering tow tank, and we'll go from there.